Welcome to StudyKwik. Today, we'll explore the relationship between Mach number, TAS, and CAS. We'll also see how this affects aircraft operation and examine the Mach airspeed indicator. Finally, we'll cover the errors affecting this combined instrument. Let's start with a climb in the standard ISA atmosphere at constant CAS. We can plot a graph to understand how TAS and Mach number change with altitude. At constant CAS, TAS increases with altitude and Mach number increases even more. Why does this happen? Air density decreases with altitude as temperature and pressure drop. Since CAS is constant, TAS must increase to compensate. At the same time, the speed of sound decreases, so Mach number rises proportionally. Flight leveling at constant CAS throughout the climb may cause the aircraft to exceed Mach limits. High-performance aircraft are flight leveling at constant CAS initially, then at constant Mach for the remainder of the climb. This ensures safe speed management. Now consider a descent at constant Mach number. Temperature increases, so LSS increases. Mach number equals TAS divided by LSS. To maintain constant Mach, TAS must also increase. Air density also increases, so CAS must increase even more than TAS. Example, at 40,000 feet, Mach equals 0.8 Mach. TAS equals 450 knots, ISA. In a constant descent at 0.8 Mach, TAS increases to 528 knots at sea level. This may exceed maximum operating speed, VMO. CAS is mainly used in the lower part of the descent. Even when Mach is constant, the sequence CAS-TAS Mach remains valid in ISA. Mnemonic CTM Chicken Tikka Masala helps recall this sequence. What happens if the atmosphere does not follow ISA? Let's climb through an inversion. In an inversion, temperature increases with altitude. LSS increases, so TAS must increase to keep Mach constant. CAS decreases in a climb through an inversion because air density reduces. In descent through an inversion, LSS and TAS decrease, CAS increases. The CTM sequence no longer applies. Next, consider a climb through an isothermal layer where temperature is constant with altitude. LSS remains constant, so TAS remains constant to maintain Mach. CAS decreases as air density drops with altitude. Now, let's look at the Mach airspeed indicator. It combines the functions of an airspeed indicator, ASI, and a Mach meter in a single instrument. There are two basic types, mechanical and electronic. Mechanical instruments use pitot-static inputs to display CAS and Mach A VMO pointer. Barber's pole indicates maximum speed. For example, Mach 0.75. The airspeed pointer shows increasing airspeed, while the Mach scale rotates proportionally. Electronic Mach airspeed indicators use an air data computer. They display Mach number and airspeed digitally. The VMO pointer is also shown as a diagonal Barber's pole. High-speed aircraft are limited to MMO, maximum Mach, and VMO, maximum operating speed. Pitot-static fed instruments follow the same principles as ASI and Mach meter. Errors from both instruments must be considered. Error types for Mach airspeed indicators. 1. Instrument error, due to friction, play, and manufacturing imperfections. 2. Position or pressure error, caused by turbulence at pitot or static sources. 3. Maneuver-induced error, temporary air pressure flight level fluctuations. Airspeed indicators also suffer from density error. This occurs because ASI reads dynamic pressure, which only equals TAS at calibrated air density. At other densities, the indicated airspeed differs from true airspeed. Compressibility error occurs at high speeds 300 knots. Air compresses in the pitot tube, causing the ASI to overread. Near the speed of sound, this error can exceed 20 knots. The Mach meter, however, does not suffer from density or compressibility errors. Its reading is based on the ratio of dynamic to static pressure. This ensures Mach readings remain accurate, even at high speeds. This concludes our lesson on the Mach TAS CAS relationship and the Mach airspeed indicator. In ISA climbs at constant CAS, TAS and Mach increase. In descent at constant Mach, TAS and CAS rise. Remember CTM, CAS to TAS to Mach. In inversions and isothermal layers, TAS and CAS behave differently, depending on air density and LSS. Mechanical and electronic Mach airspeed indicators display Mach and airspeed with maximum limits MMO and VMO. Errors include instrument, position pressure, maneuver, density, and compressibility. Thank you for watching StudyKwik. Don't forget to like, share, comment, and subscribe for more aviation lessons. Keep learning and fly safely.